Welcome to our NPTEL lectures on power quality improvement technique. We have discussed about the introduction. Today we are going to give you the overview of this power quality. So, this is the study has been done by the Georgic Power Company, and this figure number comes from the previous slide only. So, now customer perception is that 60% are neutral, whether there is a power quality or not, there is no problem, but this study is in USA. So, Indian study will be something different, and this person other 8% believes that it is due to the neighborhood, and 12% believes that it is due to the customer himself, and 70% believe that you got a power quality because of the power utility. But on the other hand, the utility people consider that most of the people are do not bother, 2/3 of this do not bother. So, others is 0, but neighbors believe that causing the power quality problem is 8%, and customer here it is 25%, here it is 12%. Customer himself believes that yes, we are the cause of concern, but utilities perception is 25% problem is created by the customer and 1% problem is created by utility. So, there is a argument in between why it is so, and customer believes that 70% problem is due to the utility. So, then we require to define. So, because the perception you have, you can see that there is a blame game some extent. Customer believes that 70% power quality problem is due to the utility, but where utility himself believes that only 1% power quality problem is due to them, rest of the 25% problem is due to the customer. So, there is a perception difference of power quality. So, thus we require to standard and to identify whose responsibility to fix it up. Otherwise, this blame game will continue. The power supply system can only control the quality of the voltage, it has no control over the current. Generally load will decide the amount of the current over the current, and that particular load might draw. Therefore, the standard in the power quality area are devoted to maintain the supply voltage within the certain limit. So, we require to maintain the voltage quality, and most of the cases we have a voltage source. Current source artificially we require to make it, otherwise we do not have a current source, and for this reason the source is voltage, and thus we require to trap there. If there is a problem of the voltage, then of course there will be a problem of the power quality. So, what is the voltage part of the power quality? The generator may provide a near perfect sine wave, very close to sine wave voltage. The current passing through the impedance of the system can cause variety of disturbances in the voltage. For example, current resulting from the short circuit cause the voltage sag to disappear completely, current from the lighting strokes passing through the power system causes high impulse of the voltage that frequently flash over the insulations and lead to the other phenomena such as short circuit or trip of the breaker. Distorted current from the harmonic producing load also distorts the voltage, since you have a source, you got a source inductance and you got a diode bridge rectifier. Though these will distort the harmonic, but due to the source inductance there will be a 7th and the 5th harmonic voltages also. So, that will distort the voltage, as they pass through the system impedances. Thus, distorted voltage is presented to the end user. If someone is here, so he will be getting a distorted voltage. So, now who is responsible, whether utility or this neighbor? So, this is a matter of perception. So, look, this is a power quality problem evaluation chart. So, you have to identify the problem category. Thereafter, we have to have a problem characterization. If it is a striking short term phenomena, it is a voltage sag. So, you have to categorize it. Then identify the range of the solution, then evaluate solution and find the optimal solution. This is the way you will proceed. For example, the voltage regulation unbalance, voltage slack, flicker, transient, harmonic distortion on the THD. These are comes under the this entity. Identify problem category. Now, problem characterization, measurement and the data collection you require to do, it is a whether it is a cause, whether it is a characteristics or the equipment impact, because THD is a equipment impact. Transient can be a flicker. So, voltage interruption may be the loss of power. Then identify the range of the solution, whether utility transmission system, who owns the responsibility, utility distribution system, end user customer interface, end user customer system, equipment design specification. So, this is all we require to revisit. And then modeling and analysis, then evaluate the technical alternative. For example, shunt active power filter can mitigate the THD problem and evaluate its economic possible solution. Why not passive, why not active? So, you can do the same thing with the passive filter, why not you go for the passive entities. So, that is also the that will be most determined by the market condition. This is evaluate the economics of the possible solution. Now, sources of the power quality problem, load equipment and components. These are, I told you previously, converters, mostly it is DC to AC, pulse modulated load, machine drives, arc furnace, computers. Now, computers standalone may be actually consuming a very less amount of load, but when you have a, for example, in our IIT Roorkee campus, we have 10,000 student. So, once they go back, everyone turn on the computer, desktop or laptop. So, those power become a harmonic power and it is not less. Thereafter, uninterrupted power supply, television sets, fluorescent light, that is also very nasty element, and other gas discharge lightings like neon, and which employs the magnetic circuits, so it will deteriorate the power quality. Subsystem of the transmission and distribution system, grounding system, that is also important, otherwise ground fault will occur, earth leakage current will flow, and also the resonance system we have to see that the leakage inductance of the inductor, and you put a capacitor for power factor correction, that may cause an interference, that may cause a resonance for the maybe fifth or seventh harmonic, and thus those harmonic will propagate fast. So, those are the issues we require to capitulate and mitigate. So, I just show you, this is a table 1, I have a separate class for the standard. So, there we have discussed in detail I just show for the sake of discussion, I just introduce it again here. Conducted low frequency phenomena, these are harmonics, interharmonics. So, what is interharmonics I will define little later if possible today. So, signal system, power line carrier, voltage fluctuation, these are flickers, voltage dip and interruption, voltage unbalance, and thereafter power frequency variations, induce low frequency voltage, DC in AC network. Thereafter radiated low frequency phenomena, magnetic field, electric field with that EMI-MC noise, conducted high frequency phenomena, induced continuous wave CW and the voltage current issues, unidirectional transient, oscillatory transient, radiated high frequency phenomena, that is due to the magnetic and electric field and electromagnetic field, as well as continuous wave and transients, and electrostatic discharge phenomena, that is ESD, mostly it is used for the electrolytic precipitator, and the nuclear magnetic pulses, that is for the NEMP. So, these are the few principle of the phenomena causing the electromagnetic disturbance, and for this you have a special standard, that is IEC. Otherwise, this is for the conducted emitted noise, and we may talk later there is a problem of EMI-EMC. But power quality is also the part of the EMI-EMC, but we generally talk about more on the THD and other issues here. For steady state phenomena, these are the following attributes can be used. These are amplitude, if there is a sag or swell of the amplitude, this is the issue of the power quality. If there is a variations of the frequency, this is the issue of the power quality. If the spectrum varies in case of the let us say, let us say you have a hysteresis control, then it will be giving a variable spectrum instead of that fixed spectrum in PWM, and that also difficult to design, thus the filters. Modulation, what kind of modulation strategy you are using, and let us say whether you are using FM or AM or something. Source impedance, it matters, because source impedance can give rise to the, if there is a current harmonic, because of the source impedance you get the voltage harmonics. And notch depth, something how much notch comes, this is the notch. So, it is flatten this voltage, and also the notch area, these are the few attributes we require to consider. If there you may be a very sharp notch for the very small interval of time, that can be eliminated very fast. And there are other power quality issue related to the non-steady state phenomena and other attributes, mainly is just transient. So, rate of rise, once you are charging a capacitor, so rate of rise of its amplitude, duration, spectrum, frequency, rate of occurrence, like you may have a notches here, thereafter after 5 cycle there will be a notches. So, that is the rate of occurrence, and its potential, energy potential. So, how much energy is associated with it. So, that is also we require to see. Essentially it may be a very high spike of high voltage, but duration is very small. So, energy potential is less. Same way the source impedance plays also an important role in rise time of these devices. Now, this is the categorize and the characteristics of the power system electromagnetic phenomena. So, this has been discussed in detail in a separate class of this standard. So, I just give you some value here, pick and choose, because detail will be done in that class only. The interruption, that is 0 to 30 cycle, and it is less than point per unit, and you can read these slides that impulse durations, it can be in microsecond, milliseconds, sag swell deep, and there are DC offset, harmonics, content, bandwidth, all those things has been discussed detail into the standard, and thus will be and thus we are skipping it. Now, transient can be classified in the two categories, one is impulsive, another is oscillatory. Now, what is impulsive transient? It is a sudden non power frequency, mind it can be any hertz, change in the steady state condition of voltage, current or both, then it is a sudden. It is unidirectional in polarity, generally it is either positive or negative. Impulsive transient are normally characterized by their rise and the decay times, which can also be revealed by their spectral content. So, you require to have a spectral analysis and you can find it out. So, what is rise time, what is delay time, what is other issues, that is wavelet. For example, so 1.2 into 50 microsecond, and that lasts for the, that is amplitude is 2000 volt. Impulsive transient normally rises from 0 to peak value 2000 volt in 1.2 microsecond, then decays half of the peak value in 50 microsecond. If you write like this, it tells like that, and most common cause of the impulsive transient is the lighting. So, this is the way we will write. So, this is the new way of writing, it is 1.2 star 50 microsecond 2000 volt. So, it means that rise time is 2000 volt and it will decay half of the peak in 50 microsecond. So, this is the example of the lighting strokes the current impulsive transient. So, it can be either of the polarity. So, you can see that it goes to some voltage or current, it is a current. So, that is in kiloampere. So, this is the rise time and you can calculate. So, what is the rise time here, and you have to calculate. So, it is around say 24. So, 12. So, what is the time here? So, this is the way it is generally classified. Now, oscillatory transient. So, a sudden, it is sudden and it is non-power frequency change in the steady state condition of voltage and current or both. It includes both positive and the negative polarity values. It consisting of a voltage and the current whose instantaneous value changes polarity rapidly. So, it described by the spectral control and it is predetermined by the frequency durations and the magnitude. The spectral control subclass is defined in class R, high, medium and the low frequency. These are the classifications of this noise. So, oscillatory transient. So, for example, if it is high frequency, primary frequency component will be 500 kilohertz, microsecond duration. So, local system response to IMPTR. Mid frequency primary frequency component will be in the range of the less than 500 kilohertz to 5 kilohertz. So, microsecond duration back to back capacitor energization that may cause this mid frequency oscillation. And the low frequency oscillation primary frequency component, it is 5 kilohertz measured in microsecond duration of 0.3 to 0.5 microsecond, and this is generally again a large capacitor bank energization. So, this is an example of the oscillatory transient. So, it will be gradually stabilizing it. So, it is due to the back to back capacitor switching. I refer my student to go to my fax devices courses. Their issues of the capacitor switching has been discussed in detail. Now, this is the example of the low frequency oscillatory transient caused by the capacitor bank energization, that is 35.4 kilobus voltage. You can see that this voltage is distorted, thereafter this voltage is distorted, thereafter again it comes to the smooth oscillatory thing. So, this is a problem for this till this point, peak of this voltage to this point. So, we had a oscillation, transitory oscillation because of the switching of the capacitor bank. Now, this is an example of the oscillatory transient caused by the ferro resonance of an unloaded transformer. So, we may have a leakage transfer A, thereafter it can react with the capacitor bank and it may have a resonance for a particular frequency, and thus what happened, maybe you got a resonance for the 7th harmonic. So, it may be generated by the adjustable speed drive, and thus it was still there, it was okay. All of a sudden you got a resonance on ferro resonance and you got a 7th harmonic oscillation, and this kind of phenomena also can be seen in case of the ferro resonance of the unloaded transformer. So, thereafter long duration voltage variations. So, these are the sacks and the soils. Long duration voltage variation encompasses root mean square deviation of power frequencies for longer than 1 minute. Then we will consider that is a long duration voltage variation. It can be either over voltage or it can be either under voltage, and it is a sustained duration, and that is more than 1 minute. Over voltage stands under voltage generally not the results of the system fault, but are caused by the local variation in the system switching operation. The long duration variations are typically displayed as a plot of RMS voltage versus the time. So, I can show you in the next few figures. So, first defined it, over voltage increases the RMS value greater than 110%, that means 10% more than the A at the power frequency of the modulation engaged for longer than 1 minute. Cause it may be due to the switching, example switching of a large load or energizing a capacitor bank. Incorrect tap settings of the transformer can also result the over voltage. Effect over voltage can cause either voltage to either the system is too weak for desired voltage regulation or voltage controls are inadequate. So, this is the reasons of it. Thereafter similarly, you can have under voltage decreases the RMS AC voltage to less than 90% of the power frequency for a duration of less than 1 minute due to switching event that are opposite of the event that causes the over voltage. Causes a load switching on the capacitor bank, switching off can cause an under voltage until voltage regulation equipment on the system can bring the voltage back to the level of tolerance or within a tolerance level. Under voltage circuits can result in the under voltages. So, another way is a power cut, that is called sustained interruption. When power supply voltage has been 0 for a period of time excess of 1 minute, the long duration voltage variation is considered a sustained interruption. This term has been defined to be the more specific regarding the absence of voltage for long period. So, now let us talk about short duration variations, and this category encompasses, this is the industrial norm in the IEC, voltage dips and the short circuit interpretations, and each type of variation can be designed as or nominated as instantaneous, momentarily and temporary depending on the durations of the table was shown in 30.2. So, here this table is 2. The fault condition that can be the cause of these power changes, the energization of the large load which require high starting current also may cause the temporary interruption. Intermittent loss of connections of the power wiring depending on the fault location and the system condition, the fault can cause either temporary voltage drops, for example, sag, voltage rise, for example, soils, or a complete loss of voltage, that is interruption. So, what is interruption? An interruption occurs when power supply voltage or the load current decreases less than 0.1 pu for a period of time not exceeding 1 minute. Causes: power system fault, equipment failure and the control malfunction. Now, interruption, the interruption can be measured by their durations, since voltage magnitude is always less than 10% of the nominal voltage value. The durations of the interruption is due to the fault of the utility system determined by the operating time of the utility protecting devices. Instantaneous reclosing generally will limit the interruption caused by the non-permanent fault is less than 30 cycles. So, 1 cycle is 20 milliseconds. So, you should be reconnect within 30 cycles, otherwise it is considered to be an interruption. So, delay of reclosing the protecting device may cause the momentarily or the temporary interruption. So, that is also a feasible entity. The durations of an interruptions is due to the equipment's malfunction or loose connection can be, the irregular pattern of the interruption can be possible. This you can see very frequent, and figure 16 shows the momentary interruption that I am showing here. So, here this is the voltage and all of a sudden it has been dropped for interruption, again it has picked up this. The 3-phase RMS voltage, a momentary interruption due to a fault at a subsequent recloser operation, and thus this is the duration of the interruption. So, we just conclude this, the delay reclosing is the of the protected devices, for example, isolator, circuit breaker, may momentarily or the temporarily give a interruption. The duration of the interruption is due to the equipment malfunction or loose connection can be irregular, and we may lose the data. And the previous figure shows that momentarily interruption during which the voltage one phase has sag about 20% is about 3 cycle and then drops to 0 and about 1.8 second and recloses back. So, this is the issue of interaction. Now, next of course, we have to talk in detail about the sag. Sag is an important features of this power quality. and there are many causes of the sag. So, we shall take this sag and the phenomena of the power quality entities in our next class. Thank you for your attention.